I spent the past 2 weeks trying to do something that I don't know if it will get any relevance, but it was intriguing to me. I was watching a video by Veritasium on YouTube about QR codes, and I wondered if I could create a way to store information on a grid-like pattern that only I can access. Even if I gave it to anyone, they would not be able to read the information on it unless I gave them the secret key or password. I am very new to cryptography, but the essence of this video is all about storing information that no one else can access unless provided with a key. The concept of encoding data in a way that is not immediately understandable to anyone who doesn't have the key to decode it piqued my interest. QR codes, which are often used to store small amounts of information in a grid-like structure, inspired me how I could go on with this idea, incorporating encryption so that even though someone might be able to access the grid, they would not be able to understand the stored information without the right key. When we talk about digital data, one of the most common types is text-based. This includes formats like text, JSON, and CSV. These formats are lightweight, human-readable, and widely used across different applications, which makes them ideal for storing and transmitting data. However, at the hardware level, all digital data is stored as binary data, which means that everything you see in a file, whether it's text or anything else, is represented by a sequence of ones and zeros. These binary sequences are not random. They follow specific character encoding standards that map binary values to readable symbols. A common encoding standard used today is the UTF-8, which is designed to represent most of the world's writing systems, and it's become the default for most applications because of its efficiency and wide compatibility. Each character you type or see is a representation of a binary number, and these binary numbers are then stored in a file. The data is typically organized into blocks or sectors on a storage device, which are read and decoded back into human-readable text when you open the file. Now, to create something similar to this, I wanted to go beyond just encoding text in a traditional way. Instead of storing the binary data as raw numbers or text, I wanted to store it visually, using square image blocks that represent zeros and ones. The process starts with converting the data into binary. Then we store it in a grid of image blocks, each representing a 0 or a 1. For example, one block could be black to represent a 1, and another block could be gray to represent a 0. But since we're going to store it on a square image file, the data length might not fit entirely in the square. So we will also use white squares to represent no data or empty spaces. This simple binary representation of the data will spread across a grid of squares and form a visual pattern that corresponds to the binary data of the original file. This is similar to how QR codes work, where each block represents a part of the data in a compact grid. Now, just having a visual grid that represents binary data is one step, but we need to ensure that the data stored in the grid is protected and not easily accessible to anyone who views it. This is where encryption comes in. The main idea is to take the original data, in this case the binary sequence, and scramble it in such a way that it becomes unreadable to anyone who doesn't have the secret key to decode it. This process works by using an algorithm that manipulates the binary data, and it could take the original data and rearrange it in a way that the resulting pattern no longer directly represents the original data. To decode the data, you would need the same secret key that was used to encrypt the grid. And with the key, the decryption process applies the inverse of the encryption algorithm. Once it is restored, the original text data can be retrieved from the binary data. The beauty of this approach is that the data is stored in a format that is inherently protected by encryption. And even though it's visually represented in a grid, it's completely unreadable without the secret key. Here's a technical breakdown on how I encoded the data with a couple of algorithms, and I decided to go big on this. I chose the AES-256 CBC algorithm to encrypt the data, where AES, or Advanced Encryption Standard, is a widely trusted symmetric encryption method, and the 256-bit key refers to the size of the key that is used with the algorithm, and due to its size, it offers robust security because there are more possible key combinations, which makes it more difficult for anyone to guess the correct key. The CBC, or the cipher block chaining mode, links each block of data to the previous ones, making it even harder to crack. So, the encryption starts with a user-provided keystring, like a password. I hash the keystring using SHA-256, which is a secure hash function that always outputs a 32-byte value, no matter the input length. Next, I generate a random 16-byte initialization vector, or the IV, and this IV ensures that even if the same data is encrypted multiple times with the same key, the output will be different each time, preventing anyone from spotting any patterns. Since the AES works on 16-byte blocks, I pad the data using PKCS7 padding to make its length a multiple of 16 bytes, and this padding adds bytes that indicate how much padding was added, which is useful for later removal. The padded data is then encrypted with the AES-256 CBC method using the hashed key and the IV, or the initialization vector, and the result is the ciphertext, which is a scrambled version of the original data. Finally, I prepend the IV to the ciphertext. This step ensures that the IV, the initialization vector, which is needed for decryption, is included with the encryption data. All the steps I've explained will give us an encrypted data that is secure, non-deterministic, and reversible when the correct key is used for decryption. Now, we take the encrypted data, which is the IV plus the ciphertext, and convert it into a sequence of bits, where each byte of the encrypted data is broken down into its 8-bit binary form. And this bit sequence is the foundation of the visual grid, as each bit will be mapped to a square. The size of the grid depends on how much data you need to encode. For a larger amount of data, the grid will need to be bigger to accommodate more binary digits. To determine the grid size, I first count how many bits need to be displayed. Since the grid must be a perfect square, I find the smallest whole number, where s squared is at least n, or greater. I do this by taking the square root of n and rounding up to the nearest whole number. Each bit gets its own cell in the grid. If the number of bits is less than the square grid, then there are extra cells left over. I fill these with white squares to mark them as unused, keeping the grid a perfect square. After all that, it's time to create the image, and for that I used Pygame, which is a Python library, to create the image, and I did so by creating a surface, which is like a digital canvas, with a size based on the grid's side length. I then draw the grid on the surface, going cell by cell. Once the grid is drawn, I save the surface as a PNG image, and this image is the final visual representation of the encrypted data. But an encrypted message is only useful if you, the intended recipient, can unlock it. So in this video, we're going to dive into the decryption process and see how to reveal the secret message hidden within this image. And the secret key, as always, is the password we used for encryption. The first step in decryption is to reverse the visual encoding. We need to read this image and convert it back into a binary sequence, which is a series of ones and zeros. Remember, in our encoding, a black square represented a 1 bit, a gray square was a 0 bit, and any white squares were just padding. We start by carefully examining the image square by square and translating the colors back into their binary equivalents. This gives us a long string of ones and zeros, which is the step back to our original message. To accurately read the grid, the system first needs to figure out the size of each individual square. We want this process to be automatic, not requiring manual guessing. And to do this, it scans the image, hunting for where the colors shift black for a 1, gray for a 0, and white as padding. It measures the consistent gaps between these changes to lock in the exact size of each square. Once it's got that, it moves square by square, translating the colors into a long string of ones and zeros, which is the binary sequence we need. Remember, the white squares were just filler to make the grid square, so they are ignored during this conversion process. They don't represent actual data bits. Once we have our bit sequence, the next step is to group these bits back into bytes. We take our long string of ones and zeros and divide it into chunks of 8 bits, where each chunk of 8 bits represents a single byte of encrypted data. Now, for the core of the decryption, we're still using the AES-256 CBC to unscramble our data. This is where our secret key, which is the password, and the initialization vector, or the IV, come into play. Let's walk through how it works. First, we take the password and run it through a hashing function, the SHA-256, as before, and this transforms the password into a precise 256-bit key that the AES needs to unlock the data. Next, we grab our byte data. The first 16 bytes are the IV, which we separate out, and the IV was mixed into the encryption process to scramble things uniquely, and we will need it to start the decryption right. The rest of the bytes are the ciphertext, or the scrambled version of our message. Now, we launch the AES-256 CBC algorithm in decryption mode. During encryption, we added something called PKCS7 padding. That padding is still there, tacked onto the end of our decrypted data. To strip it off, we look at the last byte of the decrypted output and we chop them off. This leaves us with the exact original data. Finally, the last step is to convert our decrypted binary data back into human readable text using UTF-8 encoding. And this is the same encoding we used to convert text to binary in the encryption video. And there it is, the original message revealed from our visually encrypted grid. By reversing each step of the encryption process with the correct key, we've successfully decrypted our secret message. So, that's how decryption works for our visual encryption method. I hope you found this video interesting and educational. You can explore the full code on my GitHub repository. The link is in the description below. Feel free to download the program, try it out by yourself, and even experiment with how it works. Thank you so much for watching, and if you enjoyed this video, please like and subscribe for more other fun tech projects. See you in the next video. Cheers!